This is the video introduction to parallel computing. It was created and narrated by 2015 Books Fellow Sean Krupa and accompanies the Data Analysis for Parallel Computing lesson plan created by previous fellow Jonathan Maple. This video and accompanying lesson plan are part of Ohio University's Boat of Knowledge in the Science Classroom, funded by the National Science Foundation. Let's begin by understanding the simplest form of computation. This is known as serial computation. In serial computation, a computer processor receives instructions and performs actions one at a time. This was the traditional or first method of computing and stood for a long time. The speed of a single-core processor is then simply the speed at which it can perform individual tasks. The main drawback of serial computation is speed. The larger the problem, the more individual steps that will be needed in order to solve it. Also, the only way to make serial computation faster is to perform more steps in the same amount of time. However, more steps equal more electrons equal more heat. At some point, the performance of a single-core processor is going to be limited by the tolerance of the materials it's built with to heat. It's not uncommon for a processor operating faster than it was designed to melt completely. Another drawback of serial computation are the applications or computing power it has. Only a fraction of problems are suitable for serial computation. This is because many problems in nature are complex. Additionally, you can only work on one problem at a time. In Jonathan's lesson plan, he makes a good analogy. Say you want to run PowerPoint while listening to iTunes. You don't know it, but a single-core processor is taking turns working on one program nanoseconds at a time. As long as the programs aren't too demanding, you'll never know that the computer is essentially turning one program off and one program on nanoseconds at a time. However, if you increase the number of programs or the programs have more demand, you'll experience lag or the computer might crash. Now let's look at an example of serial computing. We're going to tell our computer to take a list of random numbers and sort it into two groups, odd numbers and even numbers. In serial computation, the processor takes one number at a time, inspects it, and then puts it in the appropriate group. Now let's do an interactive example. First, we're going to tell our computer to calculate the orbit of a single planet around a single star. Do you think this is possible or not possible with serial computing? Take a few minutes to think about the problem and discuss amongst the class. Be sure to explain your reasoning. If you said this was possible, you're correct. It's possible for serial computation to solve this problem because a single planet orbiting around a single star only involves one equation that needs to be solved at a time. This is Newton's laws of gravity, of course. Now let's look at a harder problem. We're going to calculate the orbit of a single planet in a solar system made up of one star and 7 other planets. Again, we ask, is this possible or not possible with serial computation? Take a few minutes to discuss amongst the class and be sure to explain your reasoning. If you answered that this is not possible with serial computation, you're correct. The Sun and 7 other planets make up 8 equations that need to be solved simultaneously. Therefore, a single-core processor could not solve this problem. Now let's look at parallel computing. Parallel computing represents the solution to many of the drawbacks of serial computation. The basic premise is to create a processor with more than one core so that multiple tasks can be completed simultaneously, or a single task can be split up among the cores. Almost all current computers and cell phones have multi-core processors, and their names are pretty much what you would think they are. A 2-core processor is known as dual-core, 4 is quad, and 8 is octa. Here are the advantages of parallel computing. The first is speed. There is no apparent limit to the speed of parallel computing. You can simply add more cores. Also, parallel computing unlocks a lot more applications due to the increased computing power. Complex problems are now solvable. Also, problems that were hard for serial computation but possible are now simple using parallel computing. When it comes to computers, reduced time equals reduced cost. Remember Jonathan's iTunes PowerPoint analogy? Now, each core could be working on a problem or a program simultaneously. The more cores you have, the more programs or processes that can be run simultaneously, decreasing the chance of lag or crashing. There are a few drawbacks, however, to parallel computing. The first is initial cost. Processors with multiple cores require a more intricate fabrication. Also, more cores equal more chances for bugs or error in computer code. You need a reliable way to synchronize and communicate information between the cores, and telling the computer how to approach or divide the problem becomes extremely important. Let's revisit our example with the random numbers and sorting into odd and even. Now, each core takes 1/4 of the total lists and examines it simultaneously. In this simple picture, the process would now take about 1/4 the time. It's not exactly 1/4 the time because it takes the core's time to compare results and add the individual lists into 2 master lists. Let's go back to the example with the planet orbiting us in the solar system. Now when we tell our computer to calculate the orbit of a planet, say the Earth, due to the Sun and other planets, all you would need was at least an octa-core processor. Each core would solve 1/8 of the problem. Remember, the Sun and 7 planets were 8 equations that needed to be solved simultaneously, so that the correct orbit of the Earth can be represented. As we mentioned before, parallel computation is most commonly used for hard, complex problems. Here are some examples: simulating galaxy formation, planetary movements, climate models, analyzing traffic data or plate tectonics, and even weather. At this point, it's probably natural to ask, what's the most powerful computers? The simple answer are supercomputers. Supercomputers are parallel computation on steroids. Let's take a look at the Titan supercomputer, which is currently the second most powerful computer ever created. It's located at Oak Ridge National Lab in Tennessee. It was built by the United States Department of Energy in 2012 and features an astounding 299,008 total cores. The Titan supercomputer is capable of doing 10 to the 16 calculations per second. The total space it takes up is 4,300 square feet, which is enormous when considering that the average house is 2,600 square feet. Also, it cost $97 million to build. The Titan supercomputer is currently being used, or has been used, to model matter at absolute zero temperature, complex nuclear reactions, atmospheric models, and supernova explosions. Here are some take-home points from this video introduction. Parallel computing expands the capabilities of serial computation with a few drawbacks. Understanding how computers perform calculations determines what affects their speed. Now, with basic information about a computer, you should be able to make simple predictions about performance. More on this to come in Jonathan's portion of the lesson plan. This concludes the video introduction on parallel computing. If you enjoyed this video and lesson plan, there's an additional lesson plan on computer science called Understanding Computer Networks, which can be found at the web address below. Thanks for your attention.